So you will find in physicists speak, we often talk about room temperature as being ballpark 300 Kelvin. Okay? 273 is offset plus 27 Celsius gives us 300 Kelvin. Right? So Kelvin is the absolute temperature scale that we're going to use in, for example, the ideal gas equation, and to be honest, pretty much in most places in most fundamental physics. Questions, and then I'm going to ask you a few quick questions about temperatures of common objects in our universe, and then I'm going to introduce, in the remaining 10 minutes, the idea of thermal energy transfer. Questions on this stuff? Yeah?
What's standard?
What?
What's standard temperature?
Standard, what do you mean? Oh, standard temperature and pressure. Okay. I'm going to have to look this up. It's in your textbook. So standard atmospheric pressure.
It's not the same thing as room temperature.
No. Well, room temperature is kind of defined in a rather vague way. Let's let you know the answer.
I'm pretty sure it's 0 degrees Celsius.
No.
So, I don't actually remember. There's a definition of standard atmospheric pressure, which is what I introduced when I was defining those things. But then there's also standard temperature.
I think it's 298 Kelvin.
I feel it's 298 Kelvin too.
So 25
so what is
degrees.
that? 25?
25 degrees Celsius.
So these are of course just benchmarks that are used for common references. As a physicist, you generally don't care much about these things, but I should remember what they are. Go away and look up what standard temperature and pressure are. Yeah. 273.
Why is it that Kelvin doesn't have a degree symbol also?
I have no idea. So the question was, and I should just highlight it because it's often a source of confusion. The convention for Celsius and Fahrenheit is indeed, you'll see the degree symbol in front of them. You see degrees Fahrenheit and degrees Celsius. For some reason, this is not true of Kelvin. So this will, the reason I wrote it like this is, in fact, if I was writing it down, it would be that. Okay? So Kelvin does not have a degree symbol. I have no idea why. These are some of the historical artifacts that are not hugely of interest to a scientist, but maybe of interest to a historian. Yeah?
I think Kelvin is always absolute temperature, whereas Fahrenheit and Celsius can be relative, and that's why you would move the degree symbol. So with the Celsius and Fahrenheit, you have to indicate whether it's absolute or an interval temperature. Whereas Kelvin, you know it's always absolute, so that there's no reason to have the degree symbol.
I'm not sure I quite agree with your definition there. I mean, it's all a question of where the zeros are, right? So I don't know why there's no degree symbol. It doesn't matter, but there isn't one. Other questions on temperature scales? Yeah.
What is a 0 in Fahrenheit?
What is?
It's like 0 degrees in Fahrenheit. What does that mean?
In terms of physical reference points, it doesn't mean anything these days. I believe early on, you can read about this. It's interesting, but not from a scientific point of view. I believe the definition of the Fahrenheit scale actually had something to do with the temperature of the human body. So I don't know where 0 kicks into this, but it has no physical reference point on the Fahrenheit scale, okay? At least not with anything like water. Yeah?
What would absolute zero look like on a molecular scale?
Interesting question. Okay.
What would the movement
Okay, very interesting question. We're not going to talk about this much in this course, but the question was, what does 0 Kelvin look like on the molecular scale? Well, first off, let me turn that around to you and ask, what does some finite positive absolute temperature look like on the molecular scale? Vibration, right. So you might naturally assume that what's happening at the 0 point on the absolute scale is that there's no longer any atomic or molecular vibration. That would seem like a very sensible conclusion. And indeed, in classical physics, that is the correct conclusion. The classical physics turns out not to be the whole story. So in fact, quantum mechanics, for those of you who go on to learn something about quantum mechanics, will tell you that nature never commits a zero vibrational energy system, zero vibrational energy atom or molecule. So what's happening at the 0 point on the temperature scale is very interesting. It's the subject of quantum mechanics. Yes?
Why is Fahrenheit, why is it very linearly with degrees Celsius? How does that balance? Or is it just
Well, all you need are these reference points, right? So these are linear scales. They're all defined to be linear scales. So it turns out we have, what is this? This is 180 degrees between the freezing temperature of water and the boiling temperature of water. This is 100 degrees between the same two physical references. So there's the factor of 180 over 100, and there's an offset. So all you need to do, if you've got these fixed points, you can determine this conversion of linear. Because it's defined to be linear. You wouldn't define a unit that was not linear, right? In science, that would be crazy. I mean, the unit has to have the same size over all ranges, right? Otherwise, that would be crazy.
How about earthquakes though? Aren't earthquakes like?
Okay. Good point. You can take linear things, and if you've got very large dynamic ranges, you might put them on logarithmic scales, for example, for more convenience. But it's purely a convenience. Intrinsically, you're still measuring on, hopefully. In terms of the physics, what counts is a linear unit, a unit that's fixed, and you have a linear scheme for measuring. Yes?
Is it physically impossible to reach absolute zero?
Yes. Yes, it's physically impossible to reach absolute zero. It has to do with that second law of thermodynamics.
I just want to say, I think my understanding of the history of Fahrenheit is that there was one guy called Fahrenheit who was really good at making temperature scales, and he made his own scale up that 100 degrees was about the temperature of the body, and 0 degrees was about the temperature of an ice bath with salt. And he made really good thermometers.
That's right.
He sold a lot of them. And
Yes.
since he sold a lot of thermometers, it's what we use.
There you go. See, science is based on all these crazy individual accidents. So thank you. Yes, you're right. I forgot about the salted ice. That's where it is. Okay. Let me, since I'm not going to have time to talk much about change of temperature with thermal energy transfer, let's save that for Tuesday. But wrapping up, I'm going to show you one more thing, but I have questions for you, so don't pack up just yet. I want you to give me some of your general knowledge about temperature.
Oh my gosh.
So, okay, room temperature on the Kelvin scale, we usually approximate to 300 Kelvin. We can find the 0 point. Tell me about, what's the temperature of the surface of the sun?
Oh god.
5,800 Kelvin.
Yeah, you're getting close. I usually round it up to about 6,000 Kelvin, the surface of the sun. Okay, I'm not sure I can remember this one. What about the temperature of the interior of the sun? Careful reading of some notes there. It's a little bit less typically, but yes, I'll grant you that. Let's see, what else? We haven't talked about this yet, but you may have heard about it. The average temperature of, it's a bit of a hard one. It depends how you measure it. Let me be a bit more specific. The temperature of the thermally equilibrated radiation in our universe.
What?
At the back. 2.5 Kelvin. Pretty close. I'll give you that. 2.7 is changing the time, but roughly it's about 2.7 right now. What about the lowest temperature? Somebody said we can't get down to absolute zero. What about the lowest temperature achieved in human laboratories these days?
Is it like a nano-Kelvin?
Keep going.
Pico.
I don't think we're quite at femtokelvin yet. So we had nano, femto, somewhere in between. Pico. I believe we're in the picokelvin range in terms of human refrigeration, the Okay, since I have it here and I didn't show you yet, let me just show you a little bit of ideal gas behavior with liquid nitrogen. Oh yeah, what's the temperature of liquid nitrogen on the Kelvin scale? Not 140. It's cold. What's this temperature in Kelvin? No? And the reason I'm pouring on a balloon is for some physics interest, so don't ignore what's happening.
Yeah.
So I had a balloon a moment ago that looked like these ones on the desk. At about 300 Kelvin, though in this room it feels more like 350 Kelvin. I've just made it very cold. It's still at atmospheric pressure, so I've made it very cold. What would you expect would happen to a volume of gas of this size if I reduced its absolute temperature by a factor of 4, which is roughly what happens when I go from room temperature to liquid nitrogen temperature, which by the way is 78 Kelvin. You would expect that its volume would decrease by about a factor of 4. Is this a decrease in volume by about a factor of 4 compared to that?
No.
Is it more or less than a factor of 4?
More.
Okay, so why is it not following the ideal gas behavior prediction? Huh?
It's not ideal.
It's not ideal. And in particular, why has its volume become almost zero? Huh? Well, the pressure is the same, whether it's out here or in there, roughly speaking. It's on the kind of surface.
It stops being a gas.
Stop being a gas. It's actually liquefied. If you come down after class and look at this, you'll see liquid air in here. Now, of course, it's warming up. We'll be having gaseous air. So you will see liquid air inside here. Okay, we're over time. I'm going to stop there. If you guys want to come down and play with liquid nitrogen. Okay, don't do this at home. Okay, the question was, can I put my hand in
That's the only commercial.
So,